Faraday's law of electromagnetic induction and Lenz's law were both covered in GCSE, so I'm not going to go into a lot of detail about them again now. If you're a bit unsure, or actually just generally, I do suggest you look back at the GCSE material. What I am going to go into is explain the vocabulary we should be using now, and also we'll look at the equations. The summary is that changing magnetic flux can induce an EMF in a circuit, and that the induced EMF opposes the change creating it. The magnitude of the induced EMF depends on the rate of change of magnetic flux linkage, so that means speed, number of turns, and magnetic field strength are all factors. The only thing that should have caught you out a bit there was the use of the term magnetic flux linkage, so let's look into that. By the way, if you were caught out by anything else, pause this video and do a bit of review to help out. We already know magnetic flux density, which is B in the equations. This tells us the strength of the magnetic field, which is shown pictorially by the spacing of flux lines. If the lines are closer together, that is, if they are more dense, the field is stronger. If they are less dense, the field is weaker. So in this diagram, I have 3 flux lines going through an area A. We could say that B equals magnetic flux over A. And in a slightly weird twist, we're actually going to define magnetic flux, phi, as a product of magnetic flux density and area. More specifically, we should state that B is the component of the magnetic flux density perpendicular to the area A. This means that magnetic flux has units of Tesla per meter squared, or more commonly, Webers, where 1 Weber equals 1 Tesla per meter squared. Right, so magnetic induction. Bringing a magnet towards a coil induces an EMF in the coil. This is because bringing the magnet in changes the magnetic field inside the coil. When the magnet is far away like this, the magnetic flux inside the coil is small, only 3 lines in my drawing. When the magnet is close, there are more flux lines inside. We say that the magnetic flux linkage has increased. If I bring the magnet in quickly, I get a larger EMF because the rate of change of magnetic flux linkage is increased. Plotting a graph of induced EMF against time, bringing in the magnet slowly would look like this, whilst bringing it in quickly would look like this. The time is less, but the peak EMF is higher. Since the total change in magnetic flux linkage is the same though, we actually get the same area under the graph for both of these, which is something you might like to explore experimentally. This is not quite the full picture though, as adding a second turn to my coil doubles the magnetic flux linkage. I've got the same number of flux lines, but double the number of coils. Now this gives us an equation for magnetic flux linkage equals BAN, or more usefully, BAN cos theta, where theta relates to how far the field deviates from being perpendicular. And that's about it. The significant thing is you now have the tools to be able to apply these 2 laws to a wider variety of situations. So we've got the case where a magnet is moving relative to a coil, But we could also have a coil rotating in the Earth's magnetic field, or an electromagnet turning on or off, or maybe even the cross-sectional area of a coil changing. In each of these cases, all you need to know is that the EMF is equal to the rate of change of magnetic flux linkage. Following the equation, EMF equals minus BAN cos theta over delta T, with that minus sign in the equation relating to Lenz's law.